As an application for signal flow graph, we are going to represent the Thru-Reflect-Line network analyzer calibration. In a previous video, we have discussed the basic theory of the vector network analyzer, and we said that the vector network analyzer, inside the vector network analyzer, there is a 4-port reflectometer, which is used to calculate the reflected and the transmitted signals of a general 2-port network. And we said that this 4-port network has its own frequency dependent parameters, which correspond to error parameters in the calculation of the reflected and the transmitted signals. So we can represent the input port and the output port of the vector network analyzer as error box, and this error box actually add reflection and the transmission coefficients to the original reflection and transmission coefficient of the device under test. Assuming that the 4-port network or the 4-port reflectometer of the vector network analyzer is symmetric, so we can assume that the input error box has the same S parameters of the output error box, or both the 2 ports has the same S parameters. So actually, the reflected field and the transmitted field, which is calculated internally by the network analyzer, include the error box of the input port and the error box of the output port, in addition to the S parameters of the device under test. In terms of the ABCD parameters, we can say that the measured ABCD parameter, ABCD of the measure, is the ABCD of the error box multiplied by the ABCD of the device under test multiplied by the ABCD of the other error box. And because we are talking about reciprocal error box, and here the error box, this port 1 and this port 2 of the error box, here is a port 2 and here is a port 1 of the error box. In this case, the ABCD or the order of the ABCD of the second port is converted such that the D becomes in the place of A and A in the place of D. Okay. Now, this is the measured ABCD parameter. If we know the ABCD of the error box, which correspond to the S parameters or the network parameters of the direction couplers inside the network analyzer, we can obtain the ABCD of the device under test, as the ABCD of the device under test is given by ABCD to the power minus 1 multiplied by the measured ABCD multiplied by DBCA to the power minus 1. So we are going to multiply both sides by these two matrices. The remaining part here is the ABCD of the measured or the device under test directly in terms of the ABCD or the measured ABCD parameters. Once we know the ABCD of the device under test, we can obtain the corresponding S parameters. This means that it is required to find out the equivalent ABCD of the error boxes, and from the ABCD of the error boxes we can obtain the ABCD of the device under test in terms of the ABCD of the measured signal. To do this, we are going to calibrate the vector network analyzer by using known loads or known devices. Effectively, we have three unknowns in this parameter, assuming that the error box is reciprocal and if it is reciprocal, it means that S12 equal S21. So we have S11, we have S22, and we have S12. These are the three unknowns. And assuming that the two error boxes are identical, so in this case, the S parameter of the error box of the input is the same as the S parameters of the error box of the output. Okay? So we have already three unknowns: S11, S22, and S12. To obtain the solution of these three unknowns, we need three equations. Okay. The simplest calibration step is the through. The through, it means that we are going to connect port 1 to port 2 directly. In the through connection, we can represent the error box by the signal flow graph as this signal flow graph, this node A1, B1, A2, B2, and the other box, this should be A2, B2, and B2, A2 here. B2, A2 here is the total for the total structure. So we are going to call the nodes in terms of the total structure here. There is A1 is the input, if A1, and B1 is reflected, and B2 is the transmitted through the other port, and A2 is the input in the other port. Okay, this is the signal flow graph of the error box 2, and this is the signal flow graph of the error box 1, and it should be noted here that this is the reverse for this. We end here with S2 here, with S2 here, and S12 is S12 or S21 is called S12. The through connection itself is simply a line with amplitude 1. Alright? Now, by measuring the reflection and the transmission coefficient at this condition, we can say that the S11 in this case, for the through, we are going to call it T11. T11 is the reflection, which is B1 over A1. In this case, we have the bus is going from S12. We have at first a bus from S11, which is S11 of the error box, and another bus is going S12, S12 multiplied by 1 multiplied by S22 multiplied by S12. But in addition, we have a self loop here, S22 multiplied by S22. So this bus, it would be S12, S22, S12 over 1 minus S22 squared. So we have S22 multiplied by S12, S12, S12 squared, 1 over S22 squared. So this is the reflection coefficient when we are connected as through. in terms of the S parameter of the error box. Now the transmission coefficient is B2 over A1. B2 over A1, we have here the path S12 multiplied by S12, but internally we have a self loop composed of S22 squared. So this S12 multiplied by S12 squared over 1 minus S22 squared. So by using through, we have two relations. However, we have three unknowns. So we cannot solve these three unknowns by using these two equations only. We still need another calibration. Alright? It should also be noted here by the symmetry of the problem. T22 equals T11 and T21 equals T12. Alright? So at least by getting the two ports directly connected and measuring the S parameters, which is going to be called T11 and T12 in this case, according to Thru, we have two relations. Now we are going to disconnect the two ports and connecting them by unknown load with a reflection coefficient gamma L. Actually, the unknown load increasing our unknowns from 3 to 4 because we have S11, S22 and S12. Now we have, in addition to these three parameters, gamma L. So now we have 4 parameters. Until now we have two equations. Let us see what will be this additional gamma load introduced for us. If we introduce a reflection coefficient or arbitrary gamma load to port 1 and port 2, and we are going to measure the reflection and transmission coefficient. Actually, we don't have transmission coefficient in this case. We have reflection only. Alright? So the reflection coefficient is B1 over A1. In this case, from this path, we can replace it by a single loop here, gamma load multiplied by S22, and here we have gamma load. So the reflection coefficient B1 over A1 would be S11 plus S12 multiplied by S12 multiplied by gamma L over 1 minus the self loop is S22 gamma L. So the additional of gamma load has introduced a new relation, but this relation includes S11, S22 and S12 and gamma L. And from the symmetry, we can say that the reflection coefficient from port 2 would equal the reflection coefficient of port 1. We are going to call the measured reflection coefficient in this case due to the reflect connection as R11 and R22, where R11 is S11 plus S12 squared gamma L over 1 minus S22 gamma L. Now we have 3 equations in 4 unknowns. We still need another equation. So the other equation is the line connection. The line connection is to connect port 1 by port 2 through a line with length L, which you have a phase shift minus beta L, which is another unknown, because assuming that we have arbitrary length with arbitrary phase shift transmission line, but assuming that there is no attenuation. In this case, by using the signal flow graph, this is the signal flow graph of the first error box. This is the signal flow graph of the second error box. In between, they are connected by a transmission line whose phase shift e to the power minus gamma L, e to the power minus gamma L, which is the phase shift of our through the transmission line. Now we are going to measure the reflection and transmission coefficient. And because this is called according to the line, we are going to call S11 here is L11 and S21 or 12 is L12, which correspond to the reflection and transmission with the line. Alright? Now in terms of the signal flow graph, L11, which is B1 over A1, is given by S11 plus S12 multiplied by e to the power minus gamma L multiplied by S12, multiplied by S22, multiplied by S22 multiplied by e to the power minus gamma L multiplied by S12. So we have S12 squared, S22, e to the power 2 gamma L. But we have a self loop here equals S22 squared multiplied by e to the power 2 gamma L. So this is multiplied by 1 over 1 minus S22 squared e to the power minus 2 gamma L. Right? This is L11 or the measured S11 in this case. The measured S21 in this case, which is L12, is B2 over A1. B2 over A1 is S21 multiplied by e to the power minus gamma L multiplied by S12. So S12 squared e to the power minus gamma L. But we have a self loop here, which is corresponding to e to the power 2 gamma L multiplied by S22 squared. So this is S12 squared e to the power gamma minus gamma L over the ratio of the self loop 1 minus S22 squared e to the power minus 2 gamma L. Right? Now, we have unknown e to the power minus gamma L. We have unknown gamma load. We have three unknown S11, S21, and S22. And we have 5 equations. So by combining all the results of the 3 measurements, the through, the reflection, and the line, we can obtain 5 equations in 5 unknowns. So we have 5 equations in 5 unknowns. The 5 unknowns are S11, S12, S22, and the reflection coefficient gamma L, and the phase delay of the transmission line e to the power gamma L. Right? Here is S11 and S12 measured at the through. Here is S11 measured at the unknown load gamma load. Here is S11 and S12 of the line. These are the 5 measured quantities correspond to the 5 equations in the 5 unknowns. By solving these 5 equations in the 5 unknowns, we can obtain S11, S12, S22, gamma L, and e to the power minus gamma L. Right? Actually, you are interested in solving S11, S22, and S12. Once we obtain the S parameters of the error box, we can obtain the corresponding ABCD parameter. And if we obtain the ABCD parameter of the error box, we can obtain the S parameter of the unknown device under test from the measured ABCD parameter. By solving these 5 equations, we obtain S22 equal T11 minus L11, which correspond S11 at the through minus S11 at the line, over T12, which correspond S21 at the through minus L12, which is the through, S12 at the through, multiplied by e to the power minus gamma L. Effectively, e to the power minus gamma L is given by this relation, which is given in terms of L11, L12, T12, T11, L11, and so on. So we first obtain e to the power gamma L, and from e to the power gamma L we can obtain S22. From S22 we can obtain S11 as T11 minus S22 multiplied by T12. S22 is a calculated S22 here. T11 is S11 at the through, and T12 is S21 at the through. Finally, S12 squared is given by T12 minus 1 multiplied by 1 minus S22 squared, and gamma load is given by R11 minus S11 over S12 squared plus S22 multiplied by R11 minus S11. So the first term to be obtained is e to the power gamma L. Then we obtain S22, and from S22 we can obtain S11 and S12. By obtaining S11, S22, and S12, we can obtain the ABCD of the error box. From the ABCD of the error box, we extracted from the ABCD of the measured ABCD to obtain the ABCD parameter of the device under test. By obtaining the ABCD parameter of the device under test, we can obtain the S parameter or the original S parameter of the device under test by extracting the errors due to the direction couplers inside the vector network analyzer. This is briefly how to calibrate the vector network analyzer by using through, reflect, and line. Okay? Alright.